Okay, grazie. Okay, so good morning, everybody. So now, okay. So yesterday we discussed the singularity theorems, and then we showed that assuming cosmic censorship, black holes form generically as a result of gravitational collapse. So that's very nice. And then we briefly mentioned these uniqueness theorems, which basically show that if you have staticity, then Einstein's equations imply spherical symmetry, so the only solution is Schwarzschild. If you have stationarity, then you get for free axis symmetry, and therefore the curve is the only solution that you get. So this suggests that these black holes are sort of very funny. So no matter how complicated your collapse situation might have been, the final equilibrium state is parameterized by very, very few parameters in this case. So if you don't have electric charge, it's just mass and angular momentum. And that's similar like with how a thermodynamic system is parameterized by a small number of macroscopic parameters, like energy and whatever. Okay, so now what we're gonna do, we're just going to like discuss in a bit more detail this purported connection between black hole and thermodynamics. And I mean, there are a number of reviews on the market on this. You can pick and choose. One that's kind of complete, but it's a little bit, goes a little bit fast, so it doesn't go into details. It's the review by Wald in Living Reviews in GR, but okay, you can pick your favorite. Okay, so let's discuss the setup. So we want to consider a stationary black hole spacetime. And basically, in this case, it has been shown via various methods that the horizon must be a killing horizon, which basically means that it's sorry. Yeah, sorry, I don't know what the killing horizon is. So it's some sort of null surface. So being a horizon, it's a null surface to which a killing vector is perpendicular. Okay? So that's the definition. And actually, we're going to be considering non-extremal black holes. And in this case, the killing horizon is, in addition, a bifurcate killing horizon, which basically means that it looks like this. So you have a pair of null surfaces that intersect. And these null surfaces are killing horizons with respect to the same killing vector. For example, dt in Schwarzschild, this is what it does. And this intersection over here, which, in 4 dimensions is going to be a sphere, an S2. This is called the bifurcation surface, B. Okay, so this is the definition of a killing horizon. It's a null surface perpendicular to a killing vector, to which a killing vector is perpendicular. And the structure we're going to consider is this bifurcate structure. So just to give you an example that I'm sure you know very well. It's a Rindlespace. So actually, in this case, the killing horizon is not going to be an event horizon. In the case of the black holes, of course, we're going to be considering the event horizon. But in this case, as you know very well, this is just a coordinate horizon. Okay. So what is Rindlespace? So it's a patch of Minkowski space where the metric is written as such. Okay, so you can have d-dimensional Minkowski, but you're only looking at the first two directions. So I'm just going to forget about these guys. You're okay with me erasing, right? If not, you can scream. Okay, and basically the relationship between these coordinates and the usual Minkowski coordinates is that x0 is r sinh t, and x1 is r cos t. You can just compute minus dx0 squared plus dx1 squared, and you get this. Well, can people tell me what an obvious scaling vector of this is? Exactly. So dt, t goes to t plus constant, that's an isometry. So that's dt, so it's a Killing vector. But if you write these Killing vectors in terms of the original Minkowski coordinates, this is going to look like, well, so this is dx0 by dt dx0 plus dx1 by dt dx1. And from here, you see that this is dx0 by dt is x1, basically, right? So x1 dx0 plus x0 dx1, which is the boost generator in terms of the original Minkowski coordinates. Maybe I should write the original Minkowski coordinates. So this is minus dx0 squared plus dx1 squared, right? Right? This is the usual 2D Minkowski metric. And in terms of the usual isometries, of course, this is an isometry of the spacetime. This guy is just the boost generator. So now we want to look. Okay. So now what do we want to do? You see from this definition that okay. So let me just draw this Minkowski spacetime like this. So I have x1 and x0 like this. And it's easy to see that these coordinates, so you see that x1 has to be positive, just because r is positive and cos is positive. And then you also notice that x1 is greater than mod x0. Just from the definition. So basically you see that these coordinates only cover this region. Well, let me call it region 1. Okay, so you see that these coordinates, which are called Rindler coordinates, they only cover this wedge of Minkowski space, right? What else do I want to say? Good. Another thing that I want to do, that maybe I should do now, I want to introduce some null coordinates, which are big U, which is x0 plus x1, and big V, which is x0 minus x1. Is this what I want to do? Yeah. And from the definitions, you see that U is r e to the t, and V is minus r e to the minus t. Okay, just plugging this in. And basically, U and V are these null coordinates, U and V. So you see that these coordinates in terms of U and V, they cover the region where U is greater than 0 and V is smaller than 0. Okay, so now we want to show that the surface R equal to 0. So r equal to 0, as you can see from here, corresponds to either u equal to 0 or to v equal to 0, is actually a Killing horizon for this Killing vector dt. So how do we see that? So first of all, if it's a Killing horizon, the Killing vector should be normal to this surface. But since the surface is null, that means that the Killing vector should be null, right? So we should check whether xc squared is 0. So you immediately see that the norm of the Killing vector is r squared minus r squared. At r equal to 0, which means either u equal to 0 or v equal to 0. Okay, so we've recovered these two lines over here. And then, okay, very good. So, okay, good. So, and in terms of the these r and t coordinates, you see that the horizons are obtained the limit, the upper guy, which is at v equal to 0, is obtained in a limit r goes to 0 and t goes to infinity, such that this thing is fixed, whereas the past horizon is obtained in a limit r goes to 0 with t going to minus infinity, such that u goes to 0 and v is fixed. Okay? This is very similar with what happens in the Schwarzschild black hole that we discussed yesterday with this tortoise coordinate and la. This is exactly the same thing going on. Okay, so now I want to, okay, so this is, so first of all, xc is null on this surface. And then we want to show that xc is actually perpendicular to the horizon. So if xc is perpendicular to the horizon, then it should be proportional. And the horizon is an r equal to constant surface, is the r equal to 0 surface. Then it should somehow be proportional to, with the lower index, it should be proportional to, you know, dr, but okay, very good. So this guy should be proportional to the normal to the horizon, and the normal with the lower index only has an r component because this is an r equal to constant surface. Okay, and therefore with an upper index, this guy should be proportional to dr. And therefore, we should be computing dr, and dr is du by dr, du plus dv by dr, dv. And from these relations, you see that this is e to the t du minus e to the minus t dv. So we're on the future horizon, where t goes to infinity. You can just drop this term, and then you see that xc. Okay, so did I write c? Okay, I need to write one more thing. I'm sorry. So how does xc look in terms of the u and v coordinates? Well, you can do the same thing over here. So xc is du by dt du plus dv by dt dv. This is because xc is just dt. And this thing is using these relations is just u du plus minus, it's a minus v dv. People follow? Okay, good. So basically, what this is telling you is that on the future horizon, where v is 0, xc is like u du, whereas on the past horizon, where u is 0, then these guys go like minus v dv. Okay? And now you see that the same thing happens to this normal. So I had to move to coordinates which are actually good as I pass through this. Otherwise, it wouldn't make any sense. And then you see that on the future horizon, where little t goes to infinity, I can drop this term, and dr is proportional to du. So it's proportional to the killing vector over there. And similarly, on the past horizon is this term that dominates, and xc is basically given by this. Okay? So I've shown to you that in the case of the Rindler horizon, this killing vector, dt, is proportional to the normal, the null normal, to the future and the past horizon. Okay? Good. So this is what I want to say. So this is roughly the structure that one gets in the case of this bifurcate killing horizon. So here the bifurcation is just a point, or it's a line if you want to consider some transverse, extra transverse directions of Minkowski space. If people find it useful, we can also discuss the Schwarzschild case, same exercise, which also has a bifurcate killing horizon. So maybe I can do it. And you need the analytic continuation. Okay, so the metric did I keep my g's? No. Okay, very good. 2m over r dt squared plus dr squared 1 minus 2m over r plus r squared d omega 2 squared. Okay, so the horizon is a null hypersurface, and we're basically having very smart coordinates in which it will be at r equal to constant. Okay? So since it's at r equal to constant, that means that the normal, the normal to r equal to constant hypersurfaces only has a lower r index. Okay? Therefore, the norm of this guy is going to be proportional to GRR. So the norm will vanish where GRR upper RR becomes 0. And G upper RR is just the inverse of this metric component. So it's 1 minus 2m over r equal to 0. So we see that the r equal to constant surface becomes null precisely. So becomes null precisely when r equal to 2m. Okay, and now we want to, okay, so there's an obvious killing vector here, which is just dt. And we want to show that this xc is actually perpendicular to the horizon. Okay, so for that, I mean, in this coordinate system, it seems a little bit funny because the metric looks diagonal, and then the normal only has an r component. So it seems very strange that xc should be proportional to the norm. But of course, that doesn't make any sense, what I'm saying, because the coordinate system breaks down on the horizon. So I should go to good coordinates on the horizon. And those, as last time, you can go to Eddington-Finkelstein coordinates. And there, so I remind you, so we introduced the tortoise coordinate, which I'm not going to write down. You should have it from yesterday, but it was defined through something like this. dt squared minus dr star squared bless you. D r star squared, r squared d omega 2 squared. Okay, and now I'm introducing the advanced Eddington-Filkenstein coordinate, which was v, which was t plus r star. So remember, r star, because of the log, was going to minus infinity at the horizon. But I'm taking t to infinity with this guy fixed, and now I can just pass. This is a good coordinate system to go through it. And in this coordinate system, what I'm getting is, so this becomes what? dv squared minus 2 dv dr star, something like that. So I'm getting minus 1 minus 2m over r. Sorry, I already did this. dv squared plus 2 dv dr plus r squared d omega 2 squared. Good. So now, if you look at the normal in these coordinates, well, so it's still true that it only has a lower r component, because it's the r equal to constant surface. But if I raise the index, well, this is going to be, you know, n upper mu is g mu r times n lower r. Okay? And then I see that g upper mu, well, so the upper metric is going to have, so this is going to look like something like v coming from here. And that's it. No, is that it? That's it. Ah, no, sorry. G upper RR is non-zero. Yeah, right? I'm taking a 2 by 2 metric, which has something non-zero here, non-zero, non-zero, 0. The inverse metric is going to have 0 here and that non-zero over here. So G upper RR is non-zero. It's equal to plus or minus this. So plus or minus 1 minus 2m over r dr. Okay? So you see on the horizon this term vanishes. And the normal is proportional to d little v. But dt itself, if you work it out, so I introduced this new coordinates, v is t plus r star, and say r prime is equal to r. So you can immediately see that dt is dv by dt dv plus dr prime by dt dr prime. This term is 0 because r prime is just r, and this is 1. So you see that in these coordinates, the killing vector is just dv, which is proportional to n mu. Okay? I mean, this is a sort of trivial exercise, but maybe okay. If not, I'll just be doing formalism the entire hour, and you'll hate me, so at least maybe this is useful. Okay, very good. So we've shown that this killing vector is indeed perpendicular to the horizon. And now, in order to see the bifurcate the bifurcate structure that we're also seeing in Rindlespace, we really have to analytically continue, because this is how you see it. And for that, well, you go back. So remember, in order to analytically continue, you basically want to write this thing in null coordinates, which is by introducing little u. You also introduce a little u, which is t minus r star. So this thing becomes d little u, d little v. And then you notice that this part of the metric looks a little bit like flat space, like 2D flat space. And this little u and little v are basically, so it's like writing that guy as minus r squared du dv. This is basically what we're doing. So we're pulling out a redshift factor in front. And then we're having this little u and little v, which in that metric are going to be t plus minus log r, if I pull out the redshift factor. Am I making myself understood? So I'm just saying that the analog, the Rindler analogs of this T and R star, which are obtained by pulling out the redshift factor which vanishes at the horizon in front of some 2D metric, 2D flat metric. I'm saying that, so I should do the same in Rindler, pulling out an R squared, so what I'm left with is T and log R. Okay? So, in order now, in order to go back to the actual Minkowski coordinates, because this T and log R, they only cover the right wedge of Minkowski space. So in order to go back to the coordinates that are defined everywhere, you see I should define some new coordinates which are like exponentially related to this little t and log R, which are precisely these guys. So you see this is exponential of t plus log R, and similarly here. So this is what we're effectively doing in Rindler. So we want to do the same for the Schwarzschild black hole. Okay? So this is why people introduce this Kruskal. These are not exactly Kruskal, so there's some null version of Kruskal coordinates, which are defined by big U, which is minus e to the minus u over 4m. And I apologize for the fact that my favorite conventions over there are different from the favorite conventions of Sean Carroll and Wald and all these people. So, okay. So, okay. So you see that the original coordinates, little u and little v, they only cover v greater than 0 and u smaller than 0. But now, in principle, we can extend them to all values. So the structure that we were originally getting is that, okay, and that's what's different with that diagram, is that now v is this guy, and u is this guy. So we're just covering this part before. Okay? Okay, so introduce this coordinate in Schwarzschild, and then in terms of them, the metric looks something like this. M cubed over R e to the minus R over 2m du dv. Right? So this should be clear. I'm just replacing this d little u, d little v by d big U, d big V, and then taking care of the fact that the product of U and V has the difference of U and V, which is related to this tortoise coordinate R star. So I have to take care of that. And actually, the relation is something like this. It's that R over 2m minus 1 times e to the R over 2m is minus uv. Okay? Good. So, okay, so this is the Schwarzschild metric, and then you have the sphere part. Okay? And the point about writing the metric in this way is that now you can analytically continue, you know, in this entire region, which looks a little bit like a region of 2D Minkowski times the sphere. Okay, so in this form of writing the metric, you see there's absolutely no singularity at r equal to 2m. The metric is perfectly smooth, as you well know. That's a coordinate singularity, and the horizons. So the future horizon is at u equal to 0, whereas the past horizon is at v equal to 0. So it's on this line, and then your dt killing vector is something like this. Outside. Very good. Maybe I can write some more things. Okay, you can also ask what is the singularity at r equal to 0. So you see r equal to 0 is uv equal to 1. Okay? So it's something like this. This is the r equal to 0 singularity. Okay, so you should have seen this. I guess it's obliged that you've seen this in your GR class, the maximal analytic extension of the Schwarzschild black hole. If you do Penrose diagrams, then you add these pieces, and then you recognize the Penrose diagram. Okay, very good. But what I wanted to look at, I wanted to look at the scaling vector dt, and show to you that it's actually perpendicular to the horizon. So I want to look at dt, which is du by dt du. So I want to write it in terms of this null cross-cal coordinates, plus dv by dt dv. So now remember that this little v was t plus r star, and this little u is t minus r star. So only t dependence is kind of trivial inside u and v. The r dependence is super non-trivial, but the t dependence is trivial. So from here you get that this is minus u du plus v dv, sorry, divided by 4m, which comes from the exponent. Okay, and now, okay, what am I doing? What I'm doing is the following. So for example, I wanted to, what do I want to do? Questions? No. Okay, good. So it should be obvious that this guy is perpendicular to the horizon. In order to see that, so now let's do it also in these cross-cal coordinates. So basically the normal to the future horizon is this d little v, which becomes like v dv in the cross-cal coordinates, and there you see that this is exactly proportional to dt on the future horizon, because on the future horizon, I just have that. Okay? Another nice thing to notice is that, okay, so xc squared is 0 on the horizons, and that's like super obvious from this, because, well, because either u or v is 0. You also notice that xc itself is equal to 0 at the bifurcation surface. So over here, which is the point u equal to v equal to 0, the killing vector itself vanishes. Okay? So this is the fixed point of the action of xc. I forgot to say, but exactly the same thing happens in the Rindlespace. Okay? For exactly the same reason. And this is all that I want to say. Okay, so this is sort of the structure. So you see indeed that okay, in both of these cases, so you can study as many cases as you want, but okay, so these are killing horizons, and therefore this killing vector is perpendicular to the horizon, both the past one and the future one, and then you sort of see this structure that it's following this guy over here and this guy over there. Okay, good. So these were the examples. So now I just wanted to discuss a bit more abstractly some properties of killing horizons, and hopefully the example would be useful to see what happens. So some properties of killing horizons. Okay, so we want to consider a null hypersurface N. Null hypersurface. And L mu is the normal to this hypersurface. And basically, using this, one can show, okay, so because the hypersurface is null, it means that therefore L mu is perpendicular to itself, right? And therefore L mu is also tangent to N. And as such, it can be written as dx mu by dx lambda for some curve x mu of lambda inside N. Okay? Now, what one can show is that these curves are actually geodesics. So to show that, one needs to look at the geodesic equation, which is L lambda d lambda L mu. Okay, sorry. Since L mu is perpendicular to the hypersurface, that means that you can just write it. So L mu is perpendicular, that means you can write it as G mu rho d rho of some function S with some F tilde in front. So all that this is saying is that L with a lower index is proportional to the derivative of whatever function is defining that hypersurface. Okay? So now we want to plug this formula into here. And okay, good. So I'm getting d lambda okay. So now when we act with d lambda on this guy, d lambda can either act on F tilde. So we're going to get d lambda F tilde and then the rest, which is just L mu over F tilde. Okay? L mu. Or we pull out the F tilde, we pull out the G mu, nu, and then we're having d lambda d nu of S. Okay, so I just wrote L mu as such, and the derivative can act either on F tilde, case in which is a normal derivative, like a non-covariant derivative because it's just a scalar, and I pick a log F tilde, or it can act on this other part, and I can pull out G mu nu. Now, because S is a scalar, I can just switch these two indices because they commute. And now, okay, so now I can write this as good. And this term, it's basically the derivative along lambda. So it's L mu times d by d lambda F tilde, sorry, log of F tilde for this term. And then, so here what's happening, I get a d nu, so I'm going to get a d mu, okay, plus L lambda, so d mu of d lambda S, but d lambda S is just L with a lower index divided by F tilde. So it's L lambda divided by F tilde, right? This thing is just d lambda S. And now I can write this as, okay, so this term goes along for the ride, d by d lambda log F tilde. And okay. So now L lambda d mu, L lambda, I can just write it. So we played this trick yesterday. I can just write it as a half d mu L squared. Okay, so if I'm just acting on the L and just pull out the F tilde, I'm just going to get plus 1 over 2 F tilde d mu L squared. And then when the d mu is acting on the F tilde, I'm going to get minus L squared d mu F tilde over F tilde squared or something like that. Okay, this is simple algebra. if there's a mistake, I'm sure you can figure it out. Okay, very good. So, so what's happening? So what's happening is that so when I'm restricting to n, L squared is what? Sorry, L. Yeah, I didn't change my notation. What is L squared when I restrict to n? Very good. It's 0 because this is the normal to a null hypersurface, and therefore it's 0. However, this d mu of L squared is not necessarily 0 because L squared is only 0 on n. Okay? However, you can show that if you take any tangent to n, so T mu is a tangent vector to n, and then you compute this on n, it's 0 because L squared is 0 along all n. Okay? So because L squared, so L squared is 0 on n, therefore its derivative along any direction that goes along n is still going to be 0. The only thing that's not 0 are the derivatives that are orthogonal to the surface. Right? So, is this statement clear? Okay, very good. If this statement is clear, this basically means that this guy has to be proportional to L mu. Because for any tangent vector to n, then d mu L squared is perpendicular to it. Therefore, d mu L squared has to be proportional to the normal to n, and therefore this is proportional to L mu. Okay? So we get that this term over here is proportional to L mu. Okay, so basically what we're getting is that the parallelly transported L mu is going to be something proportional to L mu. So what does this mean? It basically means that it's a geodesic, but that the parameterization of the geodesic is not affine. Right? You can always change your parameterization so as to get some crap on the right-hand side of the geodesic equation. But then you know, if you're smart, you can. So basically, being smart means choosing f tilde in some appropriate way, and you choose it in such a way that the right-hand side of this equation is actually 0, such that right-hand side is equal to 0. Okay, so basically we've shown that these curves over here are actually geodesics, and these guys are called the generators of the null hypersurface N. Okay? And this is completely general. Now what we want to do is the following. So now we want to go back to killing horizons. So by definition, the killing horizon was something to which a killing vector was normal. And therefore, so we find that xi mu, which is the killing vector, has to be proportional to this L mu, which was the normal to the null hypersurface, which is the horizon. And we're going to call the proportionality constant F. And because L mu satisfies the geodesic equation, it means that xi mu also will. However, so L mu was affinely parameterized. However, we're not guaranteed that xi mu is going to be affinely parameterized. Actually, it's not. So we're going to, okay, so we have something like this. Right? So basically, this is the geodesic equation in non-affine parameterization. And this parameter k over here is basically measuring the failure of the killing vector to be affinely parameterized. Okay? And this thing is called surface gravity. Okay, so now let's understand a little bit how. Okay, so if we take this and we plug it in here, what we get is so xi mu d mu of f L mu. So you see that if the d mu is sorry, what am I doing? Nu. If the d mu is acting on L nu, you may see that we get 0 because the L mu is an affinely parameterized geodesic. So from here we get that xi mu d mu f times L nu, but L nu is xi nu divided by f. So basically I'm getting a log f over here times xi nu. Okay? Therefore k is this thing over here. Right? So we have some function f of the coordinates that's telling us how the killing vector is rescaled with respect to this affinely parameterized generator of the horizon. And this is what k is. Okay. I mean, one can derive like a zillion different formula for this surface gravity. So one that you might have seen is something like k squared is minus a half d mu xi nu d mu xi nu on n. So the way that you get this, I don't know if it's interesting, but okay. So this is, you know, it's clear that if I give you the sort of the Schwarzschild black hole and I tell you that k is given by this formula, you can just compute what it is, right? You know the metric, you know what the xi is, la la la. You can compute it. Just to give you an idea where this formula comes from, it comes from some identity like this. Which you can show painstakingly by using the fact that xi is perpendicular to n. So this is true, and then you start contracting this with d mu xi nu, and then use the definition over here. So one contraction, yeah. So it's clear that one contraction is going to give you this term into xi, and the other contraction is going to give you basically the geodesic equation into something else, and then, okay, you can massage it. The point is that you can massage it, but I don't find it interesting, so I won't do it, but just to tell you this formula exists. Another way that you can write k squared, which follows from this, is the limit as you go to this null hypersurface of minus xi mu d mu xi lambda xi nu d mu xi lambda over xi squared. So using this definition, you should immediately see this is correct. And the minus comes from the fact that, so basically what you're doing, you're going outside of the horizon. Outside the horizon, xi is time-like. And then you're taking the horizon limit. And basically the interpretation is that, so okay, maybe just think about the Schwarzschild black hole. So if I have some observer that's following the orbit of dt outside the horizon, that's an accelerated observer, right? It's sitting at r fixed in Schwarzschild coordinates, so that's an accelerated observer. And the acceleration is basically this. You can easily see when you go to specific coordinates that this is just the acceleration. So k squared is basically the acceleration squared divided by the norm of the killing vector. However, as I'm approaching, so I have to take the limit where I'm approaching the horizon. And in that limit, the acceleration of this observer diverges, right? It takes me an infinite force to keep this guy at r equals constant just outside 2m. So that thing diverges. However, if I look at this acceleration from the point of view of infinity, so basically I'm attaching the guy with some sort of string and looking at the force that I need to pull him. When I go to infinity, there's an additional redshift factor, which makes that force or that acceleration finite. And that finite number is basically this k. Okay? So basically the physical interpretation of this is that it's the force that must be exerted at infinity to hold the unit test mass in place. And this is why it's called the surface gravity. Okay, so acceleration itself diverges near the horizon, but when you do it from infinity, it's okay. So I guess you already know this, so I won't belabor the point. Very good. So very good. So I defined surface gravity. Let's work out what surface gravity is in our little examples. So for Rindler, so what shall we do? So for Rindler, what we have to do, so the simplest thing is to look at this definition over here. So you give a definition for this guy in terms of I erased. Okay, that's too bad. Okay. So basically, one way to compute this, okay, one way to compute the surface gravity is this, but I don't want to do it that way. I want to do it this way, because we already did a lot of work in Rindler to get out basically this, the relationship between xi mu and L mu. So what's happening in Rindler? So in Rindler, so if I were working, so I already derived it, so I don't want to work in terms of x naught and x1, I want to work in terms of u and v. And then I was getting something like u du plus or minus, maybe minus v dv. You should have it in your notes. So, something like that, right? So this was the killing vector. And now you want to relate it to some a finely parameterized geodesic that's along the horizon. So the question is, what is the affinely parameterized geodesic in Rindler in these coordinates? I remind you that the horizons are just the guys with u and v equal to constant. So they're these lines. And basically, the point is that the affinely parameterized geodesics are precisely du and dv. Is it clear? Okay, very good. So the affinely parameterized guys are these. So let's say that I'm along the future event horizon where I just have u du. From here, I'm just reading off the fact that this function is just big U. Okay, so xi mu is u du. This is the function, and therefore k is xi upper u, which is, its component is u, du log u, which is 1. Okay? you can do a similar exercise for Schwarzschild, where I was smart enough to leave my coordinates on the board. So here, let's say the future horizon was the guy with u equal to 0. Can somebody tell me what the extrinsic, curvature, the surface gravity of the Schwarzschild event horizon is? By staring at this formula? Very good. It's 1 over 4m. So the argument is exactly the same. The only thing that you need to realize is that at u equal to 0, dv is actually a geodesic. That's only true at u equal to 0, but you can show it. And similarly, at v equal to 0, du is a geodesic. So these guys, du and dv, are again the affinely parameterized normals to the horizon. Therefore, the function f, so along the future horizon, is just going to be v over 4m. And then you do this little calculation over here. And the 4m is going to just come from, so f, little f is v over 4m. So the 4m will stay. Okay? Over here. Therefore, k is 1 over 4m. Okay, good. So we've computed these surface gravities. And then I guess you guys are familiar with the fact that a trick to compute these guys is also another thing that you can do. You can analytically continue the geometry to Euclidean time. And then you can look at the periodicity. So you basically fix the surface gravity is related to the periodicity of the Euclidean time that's necessary for you to have a smooth geometry at r equal to 0. So you see in the Rindle case, if I analytically continue, then I'm going to get a plus r squared dt squared, the Euclidean squared. So that looks like the origin of polar coordinates. So the geometry is only smooth if the polar angle has length 2 pi. Yeah, so basically the periodicity is 2 pi times this k. In that case, k was 1. And in the Schwarzschild black hole, you can do the same exercise. I guess you guys must have done it, right? Many times. Okay, very good. So I won't do it. But basically, if you do that little exercise, you get precisely this number. Okay, very good. So now we know how to compute these extrinsic curvatures. So now we're finally ready to discuss the Zeroth Law of black hole thermodynamics. And the Zeroth law says that the surface gravity, k of a stationary black hole, is constant over the event horizon. Okay? The reason that it's called the Zeroth law is that it sounds like the Zeroth law of thermodynamics, which says that the temperature is constant. So as we'll see, this k should play some sort of role of temperature. So basically, the proof of this goes into 2 steps. You first show that k is constant along the orbits of this xi. So it's constant along each orbit. Maybe I should write the structure. So you have a bifurcate killing horizon with this xi. So you show that it's constant along, each orbit of xi. And then you show that it's actually constant all along the bifurcation sphere. And since each these orbits end at the bifurcation sphere, then you can show that it's constant everywhere. Something like that. So we're going to do step 1. So part 1 is k equals constant on orbits of C. So to show that, okay, so we're going to show, so we're going to take T to be tangent to N. And we're going to look at T lambda, d lambda k squared. Okay? What we really need is the case where T is proportional to xi lambda, right? Because we want to show that it's, so what to show this, we really need that. Right? K squared, we want to show that this is 0. That would be the statement. But I want to be a bit more general, since I'm going to need this formula later, and just consider an arbitrary tangent vector to N. Okay? And then this is, so I'm using, where is my formula for k squared? I want to use this formula for k squared. So I'm going to pick out a factor of 2. So it's minus d mu xi nu d lambda d lambda d mu xi nu. Okay? Of course, I haven't proven this formula, but you can find, by the way, a place where all these derivations are done in gory detail are some lecture notes by Townsend from like 97 on black holes and whatnot. You can find every formula that you'll ever need. Okay, very good. So you can look up the derivation. So I'm taking this, I'm plugging it into the formula for k squared. I'm getting this. And then something else that it's a little bit of a pain to prove. So I'm leaving it as an exercise, is the fact that this thing is R nu mu lambda sigma xi sigma. So this is some identity that Killing vectors satisfy. So you just use the Killing equation and the definition of the Riemann tensor, and you play with it until you get sick, and then eventually you'll be able to prove it. Okay, very good. So now we're basically done, because you see, if I take T lambda to be xi, which is what I said I wanted to do anyways, then I having two x's dotted into these two guys, but the Riemann tensor is antisymmetric in these two indices. So equals 0 for T lambda equals xi lambda by the antisymmetry of the Riemann tensor. Okay? So this proves that k is constant along the orbits of xi. And okay, now for the second step, you have to do a little bit of work. Where should I write? Maybe I should write here. Where should I write? It's just that I don't know what I'm going to need. Okay, so let me continue to write here until all hell will break loose. Okay, so for the second step, so you want to assume that k is not 0 on some orbit of xi, and basically one then shows that that this orbit only coincides with a part of the null generator. Basically, it's coinciding with this part, right? You're not doing this part. So for that, so you let xi to be d by d alpha for some parameterization, and therefore this is f times d by d lambda, which is the affine of the geodesic, and from this you get that f is d lambda by d alpha, and k from this formula, so this is d alpha log f, right? Xi is just xi alpha, so this is d alpha, which implies that f is some f0 times e to the alpha k. And this is this is a constant because along that orbit we've just proven it. But f is d lambda by d alpha. So you basically get some relationship between lambda and alpha. And by choosing f0 appropriately, you can get that lambda is plus or minus e to the k alpha, where the plus or minus depends on which side of the generator you are. Okay? But basically what this is telling you is that while alpha goes between minus infinity and infinity, you're only covering the region either lambda greater than 0 or lambda smaller than 0. So that's just part of this generator. Okay, and that's it. Very good. We've already discussed this. Okay, so this is what I wanted to get. And f is k times lambda, sorry. Am I getting this? F is k times lambda. Okay, yeah, this is what I want. Sorry. Very good. So by choosing f0 to be plus or minus k, then we get that lambda is this. And then we're plugging it back into f, d lambda by d alpha, and we're getting that f is k times e to the times plus minus e to the k alpha, but that's just lambda. So what you're getting is this. So what this means is that the killing vector xi actually has to vanish at lambda equal to 0. So of course we've seen that in the two examples, Rindler and Schwarzschild, but sort of this is a general proof that it has to vanish at lambda equal to 0, which is this point. So the alpha only covers this or only covers that, and then the killing vector has to vanish at lambda equal to 0 by this argument. And now, if you go to this surface, which is this little b, the bifurcation surface, and then you run again this argument. Yeah. So what we've done so far, we've shown that along each orbit, so along here, k is constant. We've also shown that when we get to the bifurcation surface, xi has to vanish. And now what we want to show is that k is actually constant over the entire bifurcation sphere. And if that's the case, then it's going to be, well, the same constant along each generator. So it's constant all over the horizon. Is it clear? Maybe I'm not being super clear, but that's sort of the idea. Is it clear? Okay, good. Okay, and that argument is very simple to do, because now we take any tangent to B. We're at the bifurcation surface, so now T is anything. Then we run this argument with B over here. And then we use this. So now t is arbitrary, but we've just shown that c is actually 0. So this thing is 0. Therefore, the k squared has to be a constant on the bifurcation surface. And therefore, k squared is constant over the entire horizon. Okay. So that concludes the proof. Notice that this used in a really important way the fact that we had a bifurcation point. Okay? So the proof was geometrical. We didn't use any Einstein equation, anything like that. But we used in a super essential way the fact that we had this bifurcation point. And of course, for a realistic collapse, you're not going to have a bifurcation point. So if you're interested in black holes from collapse, this is sort of useless. So people have come up with different proofs which don't use this structure. But on the other hand, they do use the Einstein equations. So you can do these proofs in like a zillion different ways. This is one of them. But there are others. Okay, good. So this is the Zeroth law. Now let's move on to the first law. So basically, the first law says that k over 2 pi times delta of the area of the event horizon over 4g Newton is delta m minus omega h delta j. I mean, if you have additional charges, you can just introduce their potentials and delta q's, and we're just going to do maximum Kerr black holes, so this is all that we're going to care about. And okay, so let's discuss it. So there are like several different ways to show this. The simplest thing that you can do, you can just take some non-stationary solutions to Einstein's equation and just compute delta A and delta M and so on between nearby solutions and check it. So we can do it in 2 lines, for example, for Schwarzschild. So for Schwarzschild, yeah. So what's the area of the horizon of Schwarzschild? It's a sphere. And then what do I write? Okay, let's do it pedagogically. Okay, so that's the Schwarzschild radius squared. So we're gonna get 16 pi g squared m squared. So and k, what was k? Yeah, it's 1 over 4 gm. If we hadn't set g to 1 in the calculation. Okay, so we can just compute. 1 over 8 pi gm times 1 over 4g. So this is k over 2 pi times 1 over 4g times delta A, which is 32 pi g squared m delta m. So the g's cancel, the pi's cancel, 8 times 4 is 32, and the m cancels, so you just get delta m. So even the factors worked out. Okay, very good. So that's the Schwarzschild black hole. That's very simple. More complicatedly, one can do this exercise for the Kerr black hole. Maybe I should ask, how many people have not seen the Kerr black hole in class? Of course. But still, I wanted to, if I understood correctly, you guys haven't seen the Penrose process. How many people have not seen the Penrose process? Okay, good. Sizable amount. Okay, very good. So I'm going to briefly discuss the Kerr black hole and the Penrose process, which is, I think historically it was a cute way that people convinced themselves that the area really increases. Okay, very good. So now let's discuss briefly the Kerr black hole. So for this, I need to write the metric, which is significantly more complicated. 2gm r over rho squared dt squared minus 4gm ar sine squared of theta over rho squared dt d phi plus rho squared of the delta dr squared plus rho squared d theta squared plus sine squared of theta over rho squared r squared plus a squared squared minus a squared delta sine squared of theta d phi squared. Okay, so this is a 4D metric where delta of r is defined to be r squared plus a squared minus 2gm r. And rho squared, which is a function of r and theta, is r squared plus a squared cos squared of theta. Okay, so far so good. So this is a space-time which has two Killing vectors, a time-like one, d by dt, and a rotational one, d by d phi. These coordinates are called Boyer-Lindquist. So there are some conserved charges associated to the two Killing vectors. QDT is just the parameter m, so you see m is just the mass of the space-time. And then the charge associated to d phi, in terms of the Kerr parameter, is just m times a. And since this is a charge associated to rotation, it's the angular momentum. Okay? And the way to compute this, you can use any formalism you like. You can use the formalism of the first lectures and look at asymptotics and plug it into the conserved charges, so you know how to do this. Right? To understand this a little bit better, so one can try to take different limits. So if you take a to 0, which means that you're taking the angular momentum to 0, what you should be getting is what are you getting? Very good. You're getting the Schwarzschild black hole because that's not rotating. If you're taking m to 0, so you're not having a black hole anymore, then what you're getting, you're going to get flat space in some funny coordinate called ellipsoidal or spheroidal coordinates. Basically, the only interesting thing that I have to say here is that r equal to 0 is not a point, but a disk of radius a. This is important because when you're studying the singularities of this metric, so we're going to discuss the horizon, of course, but that's a curve. But that's a coordinate singularity. But this metric does have a curvature singularity. The curvature singularity occurs at rho squared equal to 0. So you just compute the curvature scalars and you find. So that's basically, and in order for this obviously positive quantity to be 0, you need both r equal to 0 and theta equals pi over 2. And basically what that does is that it takes a circle inside this disk. So the singularity of Kerr, it's a ring singularity. Singularity at rho squared equal to 0 is a ring Since you guys already did the curved black hole, I'm not going to go into details, but this was done in class, I guess. Okay? And then you can analytically continue through the singularity way. You analytically continue through the horizons, and then past the singularities, you find some closed time-like curves. You can go to parallel universes and all this beautiful stuff, right? What was it? So you have this structure, right? So these are the ring singularities. You come from here, scribe minus to scribe plus. This is R plus, this is R minus. You go inside the horizon. Then you go inside the inner horizon. Then you can go here, and there's another asymptotically flat region, but it's full of closed time-like curves, so it's really bad, but you can just go on and on and on and never get out. Of course, the structure is bullshit because if you put a little bit of matter, you're going to destroy, the inner horizon is unstable. But anyways, I said I wouldn't discuss this. Okay, very good. So let's discuss something more serious. So let's see where the horizon is. So again, via some magic, the horizon is going to be an R equal to constant surface. So let's see when the normal to the surface becomes null. For that, I need to compute G upper RR, and G upper RR is delta over rho squared. Therefore, it's 0 when this quantity is 0. So I get R plus minus equals Gm plus minus square root of Gm. Okay, I'm just solving this quadratic equation. So I'm getting an outer and an inner horizon. Maybe I should draw them. So I have an R plus, then I have an R minus, then I have some funny ring singularity over here. Of course, in order for the square root to make sense, I need A to be smaller in absolute value than G times M. If not, I'm starting to get naked singularities and all sorts of other crap. So I want that restriction. So there's a maximum amount of spin of a curved black hole. And those maximally spinning black holes are actually very interesting. They have a lot of nice structure. Okay, very good. But this metric has another interesting feature. Okay, so now let's compute GTT at R plus. So GTT at R plus, you can compute it, is minus rho squared, which is R plus squared plus A squared cos squared of theta minus 2gm R plus over rho squared of R plus. And now, since I'm at the horizon, R plus squared minus 2gm R plus is minus A squared, right? So basically, this whole thing is I'm going to get a minus A squared from here, plus A squared cos squared of theta. So that's minus minus, it's A squared sine squared of theta over rho squared. So, well, it's greater or equal to 0 because at theta equal to 0 and pi, of course, it's 0. But basically, this is showing you that the horizon, so I said that it had to be a killing horizon, but it's not going to be a killing horizon for dt, because dt is not null on the horizon. So it's interesting to ask when does dt become null. It's going to become null outside of the horizon because it's already of positive norm once you reach it. And so we want to, so GTT equal to 0, which is basically GTT is the norm of dt squared. Well, for that, I need to solve rho squared equals 2gmr. So the surface where GTT is 0 is called the ergosphere, or the boundary of the ergosphere, and that's going to be given by gm plus square root of g squared m squared minus a squared cos squared of theta, which is outside R plus. Well, is this clear? So I'm just asking when does this thing become 0? This is the solution, and you just compare it. I'm subtracting less from here. Therefore, the place where dt can become space-like, becomes null, and then it will become space-like, is outside the horizon. So it's this surface over here. Oh, terrible. Can anybody see this? This is a terrible drawing, but you get the idea, right? It depends on theta. It touches the horizon at theta equals to 0 and pi, where you get the same expression, but more generally, it's sort of bulging out. So this is the region where dt is space-like. Okay, and this is a very interesting feature of these rotating black holes. They generally have these ergospheres. So the funny thing, so once you enter the ergosphere, you're actually forced to co-rotate with the horizon. So the way that you see that is that if you go over here, so inside the ergosphere, this term is positive. This term is also positive. So the only way for you to be actually a time-like observer is if d phi by d tau is non-zero and sufficiently positive. Okay, that's the only way to actually make this piece of the metric time-like. Okay. So inside must co-rotate in the same direction as the black hole. So you see the sign of d phi by d tau is fixed. Okay? Okay, so you may wonder then, okay, so what if, you know, in the case of the Schwarzschild black hole, one could just consider some observers which are sort of static outside the black hole horizon at fixed R. But now you cannot do that anymore because all the observers that are close to the horizon, so that are inside the ergosphere, must rotate to the black hole. So what can you do? So the closest thing that you can get to a static observer is something called a locally non-rotating observer, and their forward velocity is proportional to d mu t. Okay? And from these, you can see, so if you define their velocity, omega to be d phi by dt. Okay, so this is d phi by d tau divided by dt by d tau for those observers. So from here, you see that u with a lower index must be, this mu has to be a t index, right? So this thing must be proportional, must equal g phi t divided by g t t. I'm just saying that the forward velocity of these guys, the only non-zero lower component is t. So from that, you get this. And apparently, this is minus GT phi by GTT, if you know how to invert matrices. And now, let's just plug in what that is. So that's 2GMAR okay, what am I doing? Okay. Divided by GTT, which is, oh my God. Okay, let's do it at the horizon. Because, okay, so now let me compute it at the horizon. So at R plus. I mean, in general, you can compute them at any R, but I'm lazy. So now I want to get the GTT at R plus, which supposedly I already computed, which is A squared sine squared of theta over rho squared. And okay. You guys didn't tell me that I made a mistake. So when you invert a matrix, A, B, C, D minus 1 is 1 over the determinant dA, right? So this is minus GT phi divided by G phi phi. Okay, and now I'll just copy it because I don't want to make more mistakes. RA over R squared plus A squared squared minus delta A squared sine squared of theta. Yeah, which is obvious from that formula. And when you're going to the horizon, so you can define omega h, which is omega at R plus. And at R plus, delta is 0. And 2m R plus is R squared, R plus squared plus A squared. So you're just picking A over R plus squared plus A squared. So this is the angular velocity of this locally non-rotating observer, which is sitting right above the horizon. And sort of for this reason, this thing is called the angular velocity of the horizon. Okay? Very good. And now you define this omega h, so one can show, so this horizon is the Killing horizon with respect to some Killing vector. The Killing vector is just dt plus omega h d phi. So you can easily check the x squared on the horizon is 0, and it's also is normal. All the stuff that we did for Schwarzschild and so on, it also works here. Okay, very good. So, so this is the structure. So the important new structure in the case of the Kerr black hole is that you're getting this this ergosphere, and interesting things can happen once you're in the ergosphere. Which is, for example, this Penrose process. And, okay. So basically, what Penrose showed is that when you have an ergosphere, you can actually extract energy from the black hole for the following reason. Well, the reason is that inside the ergosphere, so you're not inside the horizon, you can get out if you want. But inside the ergosphere, dt is space-like. Therefore, the sort of conserved energy sort of associated to dt. So you're considering some particles world line, so you can define E, which is just P mu times dt mu. Okay, so that's the conserved quantity associated to this Killing vector. There's a minus because in Minkowski, in asymptotically flat, you want energies to be positive. So P mu is time-like, dt is time-like. So for both of them time-like, you want the energy to be positive. So this is why you put a minus sign. Okay. So when both of these guys are time-like, this has to be positive. However, you see that inside the ergosphere, dt is space-like. Therefore, there's no more restriction on the sign of E. Okay? So inside the ergosphere, because dt is space-like, E can be negative. Okay? So now the basic idea is, okay, so you have particles which have this sort of killing energy, which is negative. Of course, these particles have to sit inside the ergosphere, so they cannot get out because once they're out of the ergosphere, they should have positive energy. So they're sort of stuck over there. Or another thing you can do, you can just kick them, and then you're increasing the energy to something positive, and then they can get out. Stuck inside the ergosphere, they can just exist. They can fall inside the event horizon if they want, but they don't need to, and so on. Very good. So the basic idea behind this Penrose process is to cook up a situation where you're sending some particle from infinity, and well, let me actually draw. So this is the event horizon, this is the ergosphere, and you're sending some particle from infinity to go inside the ergosphere, and there it explodes into two pieces, and you're cooking up the explosion in such a way that the energy of one of the particles is negative. The energy with respect to the dt killing vector is negative. So then by energy conservation, the other guy, which can get out, is going to have larger energy than it went in with. Okay? So basically, okay, so you have some P0, which is coming in. Here it splits into some P1 and some P2. By energy conservation, energy momentum conservation, you should have this. But now when you're taking the dot product with dt, so of course this implies that E0 is E1 plus E2. But now in principle you can have E2 negative, which implies that E1 is greater than E0. So your particle has come back with larger energy that you sent it in with, and that's really cool. I should say this is not just some mathematical construct. Let's play with black holes. So black holes oftentimes they emit some really powerful jets. So I guess one is talking about black holes with accretion disks, and then they have some, I think they go for millions of light years, so they're really powerful, and it is believed that it's sort of this process that fuels them. But I don't think it's proven. So this is not of just theoretical interest. There might be very nice processes in astrophysics that actually have to do with some really fancy version of this mechanism. Very good. So this is a proof of principle. So then you might say, oh my God, so I can just send in my particles and then extract the entire energy of the black hole, eat up my black hole, what's going to happen? But actually it turns out that there is a limit to how much energy you can actually extract. And that limit comes from the fact that this other particle, which the way that you're arranging it, it can fall inside the horizon, And the horizon, so it's orthogonal to this null killing vector, which is future directed. So this guy is future directed null. This guy is time-like, future directed. Therefore, their dot product, so xi mu, p2 mu, should be negative in my conventions. Okay? But as I told you, xi is dt plus omega d phi, so this implies that, so dt into p2 mu is minus e2 plus omega h d phi into p2 is j2. So this has to be smaller than 0, which implies that j2 has to be smaller than e2 over omega h, which is smaller than 0. Okay, so basically what this is showing you is that the way that this explosion should be arranged is such that the angular momentum of this P2, you should try to aim it against the rotation of the black hole. And then there's this inequality that it has to satisfy. Okay, very good. So the last thing that I wanted to see. So basically, this is telling you that since J2 is negative, the way that you're extracting the energy is that you're lowering the angular momentum of the black hole. Okay. So this already tells you how much energy that you can extract. So the more that you do this, the slower that your black hole is going to rotate. At some point, it's going to stop rotating, and then you cannot extract anything anymore from it. And I think the first person who studied this was Christodoulou. So he was looking at limits on energy extraction from these guys. And you can show, okay, so what can you show? So I told you that a really dumb way to look at the first law is to just check that it holds between nearby solutions. So it's something like k to the 2 pi delta AH over 4G is delta M minus omega H delta J. So for the Kerr black hole, you can just take the solution and just plug in and do the variations for two nearby Kerr solutions. It's trivial, but it takes a bit of time. So, but this is true, you can check it. And now let's see what happens to the variation of the horizon area in this Penrose process. Okay? So delta M is negative, it's just E2, right? Which is negative. Minus omega H delta J. And, okay, sorry. So this thing is E2 minus omega H J2. And then we see from here that this is just the negative of this inequality over here. Therefore, this thing is positive. So even in this really funny process where you're extracting energy of the black hole, you have some quantity that increases, which is the area of the event horizon. And I guess this was one of the first, well, there are other hints, but this was an important hint that, this is some quantity that always increases, just like, which made it a natural candidate for an entropy, which also always increases. Okay, good. So this was the Penrose process. So maybe we can take a break.